Okay. Last class, I left with this recurrence that described Karatsuba, and we had come up with this tree and this calculation to give us a sense of what the recurrence would solve to. And we had come up with this asymptotic solution, which was better than the n-squared algorithm. But when we came to the guess and check proof, we actually only proved this bound, just to get a sense of the technique. So now I'm going to give a guess and check proof for that recurrence that gives the tight asymptotic upper bound here. So how would that work? So what I'm going to do here is prove that T of n is upper bounded by, I'm going to change that constant to 18n. By inspection, the statement holds. I'll talk about by inspection in a second, but for now, by inspection, we can plug in a few values and notice that this is going to work for small n. Suppose that it holds for all n less than n0. Consider T of n0 plus 1. The first step of these type of induction arguments are to substitute in exactly this statement into the definition of the recurrence. So that's 3 times T of n0 plus 1 over 2 plus 9 times n0 plus 1. And now we can conclude that this is going to be n0 plus 1 over 2 raised to the log base 2 of 3 minus 18 times n0 plus 1 over 2 plus 9 times n0 plus 1. And now we're just going to simplify this. We're going to move 2 to the log base 2 of 3 is 3. So this is just going to be 3 over 3 times n0 plus 1 to the log base 2 of 3 minus, and now I'm going to multiply this out, n0 plus 1 to the log base 2 of 3 minus 18 times n0 plus 1. So that's a clean argument for why this recurrence, if I set the appropriate base conditions. So if we strip away some of the details like this base cases, this is a logical structure of the argument. And now notice why I had to use 18n in here. I believe I left last class with 16n because I had this instead of 9, it was 8. But I know you have a lot of questions. Questions like, how did you come up with this minus 18n? Questions like, well, what about the base case? When you run this algorithm on a small instance, it's actually not, T of 2 isn't actually 1. It's like 4 or 9 or 12. How to actually solve these type of problems in practice? Let me address all of those questions with a further refinement of this argument. Imagine we wanted to do a really concrete analysis of this type of Karatsuba's algorithm. So what we'd do is we'd consider, remember we said that the base case for Karatsuba was n equal 2. When we talk about two-digit numbers that we're multiplying, we're just going to multiply these 4 operations. We're just going to do 4 multiplications and 3 additions. And now imagine I wrote a program and I inspected the assembly language instructions that came up for multiplying two-digit by two-digit numbers. And I discovered that when I multiplied two-digit by two-digit numbers, it took me 10 operations. I'm just picking that number 10. It's a reasonable number. I've done it once before. You're with me. So before I had always said like T of 0 is equal to 1 or T of 0 is equal to 2. I've always picked them so that my analysis works out. And I know that you're often very concerned about the fact that in real life these aren't the numbers. And so I want to go through an example where the numbers are actually quite reasonable and practical. You know, the base case is T of 2 is equal to 10. Now let's consider 4. By the Karatsuba algorithm, right, we did 3 operations on T of 2, right? And then we combined. And so the number of operations would be 3 times T of 2 plus whatever number this was in the actual assembly. So that's 3 times 10 plus, I believe this was 32 operations when I did the analysis. So I would conclude that T of 4 is equal to 62. Here's what I did. I considered our Karatsuba algorithm and I ran it for digits 2, 4, 8, 16, all the way up to, let's say, 128. And I actually counted the number of operations that we would consume there. Everybody with me? The next step I did is I actually fit a function and it looks exactly like this, that matches all of these particular numbers in practice. When we were throwing away constants, we just had sort of, n log squared n minus, minus 18n or something. But when we actually sort of count the number of instructions, it's something like this. And I've always told you this doesn't matter if we had a 14 or a 16 or an 18 and so forth. Here is sort of evidence of why it doesn't matter. So what we're going to do now, prove by induction that t of n is less than or equal to 14n. Let me get you through the first step. So by inspection, and this is what I mean by inspection. By inspection I mean I actually looked at the algorithm and I did the examples and I counted exactly the set of instructions, and I noticed that this function right here is an upper bound on t of, I actually did it up to 1024. And now what would be the very next step of this proof? These proofs have 4 sentences. What's the next sentence? Consider. So by inspection, we're basically saying that this statement holds for all n that's less than 1024. Let's consider n 0 plus 1. What's the very next sentence we do? Plug it in. Here we're using 8 again. Again, we're going to conclude exactly the same steps as before, except this time we plug in 14n to the log base 2 of 3. So the constants have just become a little bit more aggressive, more specific here, but it's exactly the same argument. And I want to try to, once you do this a few times, your intuition will build so that you'll understand when you can sort of fudge with constants and when you can't, when they matter and when they don't. I'll step through the analysis here. It's exactly the same. Okay, so all we're going to do is analyze this right here by pulling out the 2 right here and bringing that to the 3. And you can sort of see that this right here is going to sum up to exactly 16n again. And step through this analysis. So this is the induction proof in full, in all of the steps with nothing missing, and also typed so you can read my handwriting. It does matter, and in this case, since our assumption here was less than or equal, all of these things should be less than or equal as well. The assumption and the conclusion. So notice our conclusion right here is that this statement holds for tn of 0 plus 1, and that has to be the same as our assumption. So if it's less than over here, it has to be less than over there. I've gone over that once more. You see that this is an upper bound, and so we can conclude that t of n is O of n to the log base 2 of 3, right? Since this is n to the log base 2 of 3 minus a lower order term. To test your understanding of this technique, what happens in our proof if we did not have that minus 16n? If our inductive hypothesis didn't have that, where would we come to an error, and why would we be able to stop? I'm going to walk through the first few steps of the argument, and then you're going to pair up and try to explain to each other what happens, what goes wrong. So here's the algorithm. Here's the argument. Just like before, let's prove that t of n is upper bounded by 14 log base 2 of 3 without the minus 16n. So again, by inspection, we've discovered that since it holds that t of n is upper bounded by 14n minus 16n, it certainly also holds that it's upper bounded by just 14n to the log base 2 of 3. If it was greater than blah minus 16n, then it's certainly greater than just blah. Assumption 1, let's assume that t of n is upper bounded by this whenever n is less than n0. And now let's, as before, consider the case of n0 plus 1. Let's take our formula, expand it out according to exactly what the definition of the recurrence is. Let's therefore conclude that because n0 plus 1 over 2 is less than n0, we can substitute in our formula. These are exactly the steps we would go through. And now I want you to pair up with someone, 2 or 3 people, and try to explain how to continue this proof, or in particular, what goes wrong, why you can't continue. So I was roaming around the room, and I think many of you came to this conclusion that, yeah, of course, these 3's will cancel out, and we'll end up with the expression just like this, that n0 plus 1 to the log base 2 of 3 plus 8n0 plus 1. Problem is by basically concluding this. And that's not how induction works. Induction works by saying the same property holds for the first n cases, and now I'm going to show that the same property holds for n plus 1 case. I can apply that same meta argument again. Now that it's true for n plus 1 cases, it'll be true for n plus 2 cases and 3, etc., etc. But for you to apply the same argument to the n plus 0, n plus 1 cases, n plus 2 cases, you have to be proving exactly the same property that you're assuming. If you assume it's true for the first n cases, you need to prove that it's also true for the n plus first case. So this statement has to be exactly the same as this statement for induction to work. You can certainly have a stronger statement here, okay, that implies this statement, but this statement, the assuming statement has to at least be true. And so in this case, changing 14n to 100 million doesn't get rid of the problem. To get around this problem, you have this extra nasty term. Well, this is how you do it. You try to work it out yourself like this, and you come to the problem. You come to the observation that this assumption is not the same as my conclusion. And my conclusion has this unfortunate 8 times n0 plus 1 term, which I have to remove somehow. I have to make this term negative. So the only way I can do that is to change my assumption by subtracting something that's larger than 8n plus 1. This problem. Once you come to this problem in your homework, the way to get around it is to figure out what you need to get rid of and then change your assumption. Make a stronger assumption up here, and then that helps you prove this statement. Question. But to make this proof work, you had to pick these two constants, 14 and 16. 14 and 16 were in particular meant to fit the real data that I had collected before on this algorithm. So what I have shown is that 14, what you're arguing is that 14 log base 2 of 3 minus 16n is in. And so therefore, it's true that this is upper bounded by, right? This is the argument you're making. Well, this function's in O of log, so that means that there exists some C such that this function is upper bounded by this. That is true. That's the last step of the proof. But the part of the proof that we're working on is showing that T of n is upper bounded by this function, from which we can then conclude that it's in O of n to the log base. Sense? Question. Go through the same exact argument, except instead of 14, put the letter A, and instead of 16, put the letter B, and you can go through and then you can conclude what A and B have to be in relation for this to work. Question? Exactly. In particular, it implies it. If I'm less than 80 minus 40, then I'm certainly less than 80. Question in the back. Yes, that's the beauty of induction proofs. You can have it all messy in your head and then just come up with a nice argument I can read quickly and determine if you know what you're talking about. To come up with it's exactly right. You use the tree method to get the answer, to sort of get the intuition, and then use this guess and check induction method to give a short proof. It's exactly right. Okay, here's one you can do at home. Here is another tool set that you're going to use. Okay, it's a cookbook method. When the recurrence is of a very special form, which is going to occur quite often in this class, you can use what's called the Master's theorem. And here is the idea. Look at that recurrence. It's going to be a popular type of recurrence that we encounter. Many algorithms are going to break the problem into chunks of size n over b, create a of them, and then use f of n work in order to glue them all together. This is something we're going to see a lot. We're going to find a solution for recurrences that are of this form. T of n is equal to a times t of n over b plus f of n. And we are going to do it exactly how we've done every other recurrence in this class. We are first going to draw a tree, add up all the work, and then use an induction argument to show what the answer has to be. Except, instead of using constants here, as I suggested earlier, we are just going to put in a, b, and f for these type of things. So let's go ahead and get started. Just like before, I'm going to create a little box right here to represent that this is the amount of work that we're going to do for t of n, and that's going to be f of n right here, plus a different calls to boxes of size t of n over b. And then each of those will also have a children. So let's go ahead and, as before, express how much work is involved. At that first level, when we call t of n, we're going to be doing f of n work. And then there were a recursive calls, each of size n over b, and so each of these are going to have f of n over b, and so we have f of n over b. Now at the second level of this recursion, each of these nodes are t of n over b squared, and the amount of work that there's going to do is f of n over b squared. Okay? And so at this second level, this was this level, we're going to have a squared times f of n over b squared work. Just as before, eventually we're going to get to a base case, and the number of levels here is going to be what? Log, which base? B of n. So at that level, we're going to have a to the L, and they're going to be interacting on problems of size b to the L there, right? So let's just, as before, write a summation for what t of n is. This should be familiar because it's exactly like the last three examples, except I've just put f of n where before we had concrete functions, and I just put a and b where before we had constants there. So now, here's where the Master's theorem comes in. This summation, one of three things can happen. Because we haven't specified what f is and what a and b are, there are essentially three things that can happen. Either the amount of work that happens progressively gets larger and larger so that all the work happens at the leaf. So if these boxes right here are supposed to represent the work that each of these terms represents, and we can imagine that f of n is a rather small function, and that essentially as you recurse, you create more and more, your tree gets larger and larger, such that most of the work is happening at the very bottom of the tree. The second case that could happen is that all of these are roughly the same. And what's the third thing that could happen? You did all your work at the beginning of your life, and then it progressively got easier, such that by the end, you had nothing to do. Good point. So this Master's theorem is meant to model like well-behaved functions that occur in the type of algorithms that we're going to encounter. So you could imagine f is one of these crazy functions. If f is applied on a prime number, it does all sorts of stuff. If it's a not prime number, it basically is 1. It could be a very crazy function like this, and then our Master's theorem won't work. So when f is kind of a well-behaved function, these are the three cases the Master's theorem is going to consider. All right. So let's handle each of these cases one by one, starting with this case right here. Okay, so our theorem is going to be like this. When f of n is equal to O of n to the log base b of a minus epsilon, then t is going to be theta of n to the log base b of a. This is our cookbook. Remember I said in class it's not going to be like a situation where you have a projectile launched at 30 degrees with this velocity and it end up right there. There's no formula for that. Here is one of the very few cookbook formulas. If f looks like this, then t looks like that. No induction, No guess and check method, just the cookbook method. So let me give you an example of something like this. This is n squared. So in particular, let's talk about what it means for something to be n to the log base b of a minus epsilon. What does that mean? This is n squared. This is n to the 1.97. So this function right here is O of n squared minus epsilon, where epsilon is basically 0.003. So it's a very specific type of notion of asymptotic dominance. This function right here is asymptotically dominated by n squared by this polynomial factor of epsilon. Let's consider an example like this. Let's identify the parts. What is f of n in this situation? N, exactly. What is a in this situation? 4, and b is 2. So O of n of log base 2 of 4 minus epsilon is equal to O of n squared minus epsilon. And so now we have to ask, is n in O of n squared minus epsilon? And the answer is yes. Set epsilon to, anything that's like that right there is certainly true, right? Even if we set it to 0.91, it'll be true. Given the recurrence, we separate out what f of n is, what a and b are, and we check whether f of n is in this right here. In this case, it is, and so that means right away that t of n is going to be theta of n to the log base 2 of 4, or theta of n squared. No fiddling around, just that. And now, where does this expression come from? What problem have we studied that has that kind of recurrence? Not merge sort. School book multiplication. Remember from lecture 2. Except there it was, we had 3n, right? But notice that wouldn't matter here. If we put a 3n here, it would still be in this right here. In fact, if we had 100n, it would still be in there. The only thing that mattered here was a and b. Once you get a hold of these type of simple facts and they really become natural to you, algorithms will become very simple. You can really forget about a lot of the details and get to the heart of something. Question in the back. Exactly. The epsilon doesn't matter. This is just a way of saying that this is just a really formal way of saying the amount of work that you're going to do because of this part is just way more than the amount of work you're doing for this part. The amount of work that you're going to do for this part right here is going to be like log to the n to the log base 2 of 4, okay? And so as long as this stuff right here is way smaller, asymptotically smaller, that's what it means by this minus epsilon, then it's not going to affect the higher order term. Now let's go through this argument. Let's see why this is true. How are we going to show this theorem is true? Case 1, f of n is like this. So in particular, that implies that f of n is upper bounded by c times n to the log base b of a minus epsilon. So that means that we can rewrite t of n as c times n to the log base b of a minus epsilon plus a times c times n over b to the log base b of a minus epsilon plus a squared times c of n over b squared to the log base b of a minus epsilon plus a to the L minus 1 times c of n over b to the L minus 1 to the log base b of a minus epsilon plus, and then at this very last term, I'm just going to put a to the L. And now all I'm going to do, so all I did there was write out every term. I know that all of you are capable of doing that. This is discrete math test. So now what I'm going to do, another very basic math step. I'm just going to factor out, this nasty term, c times log base b of a minus epsilon. And I'm just going to write this in something that we know how to tackle, which is 1 plus Now this is going to be a over b to the log base b of a minus epsilon plus a squared over b squared to the log base b of a minus epsilon, a to the L minus 1 over b to the L minus 1 to the log base b of a minus epsilon. And then I'm just going to write, again, a to the L times f of 1 right here. So at this point, I need to do a few simplifications here. First, remind me from lecture 1 what this summation is. Now I need 3 more facts. So the first thing is, look at all of these funny terms right here. Let's simplify them. So if I have a to the I over b to the I times log base b of a minus epsilon, I want to simplify that. And the first thing I'm going to do is this standard trick I love to do, which is move these exponents around. So this is b to the log base b of a is going to, what's b to the log base b of a? A. So that's going to be a to the I over a to the I over b to the epsilon I. That is just going to be b to the epsilon I. Question? Okay, so first, previous page? Okay, and you would like me to explain this part right here? Okay, so this very last term of this expression is going to be a to the L, and it's going to be n over b to the L, where we define L so that b to the L is roughly runs to, we define the recursion so it goes all the way until f is applied on a base case, a unit case. So this will just be f of 1, and so this will just be a to the L applied to f of 1. I'm just making a special case for it. Because essentially n over b to the L is going to be 1. We run this recursion until the base case when it's, recursion stops when it's a problem of size 1 or constant. That's fact 1. Now I want to do fact 2, a to the L, which goes to your point right there. So this is a raised to the log base b of a. Okay? Oh, sorry. Log base b of n. Remember, L is the number of levels. And now I would like you, in a minute, to figure out what this is with respect to n. Use your neighbor. Spend a minute. Tell me what I should write right there. So here's how I solve this problem. I want to write a into something that's like b to something, right? So a I can rewrite as b to the log base b of a, and then just keep that exponent right there, right? This right here is equal to a. And then, as before, I just flip these exponents around, put the log b to the n inside, and then this right here, I just simplify to n. Okay, so a to the L is like that term right there. And now b to the L, so what I want to do is, even if I put an epsilon here, I'll get this right here. So b to the epsilon L is equal to n to the epsilon. So this is basically equal to n to the epsilon minus 1 over b to the epsilon minus 1. Now with these 3 facts, I can dramatically simplify this previous expression that I have. In particular, each of these terms right here simplifies to b to the epsilon I, right? So this is if I just apply these 3 simplifications, I get raise your hand if you understand how I went from here to here. We good? So not everybody. And ask me some questions then. Right? All I did is take expression 1 right there. Each of these little funny terms right here, I just applied expression 1 to get this right here. Now what am I going to do next? I'm going to apply expression 2 to this term right here and get this. To put it all together, I'm going to, that very top line right there is exactly what this summation is right here. And so I can conclude that that's equal to n to the epsilon minus 1 times some constant c. I'm not even going to figure that one out. Just b to the epsilon minus 1 plus n to the log base b of a times, again, some constant f of 1. Why is this important? Because now all of a sudden we have n to the log base b of a minus epsilon times n to the epsilon right here. So it's just c times n to the log base b of a. I'm going to change this constant, make it a c prime. And that c prime is going to take this c in account and this f1. I'm just going to add those two. And then I'm going to subtract off c times double prime. Right? I needed to deal with this minus 1c right there, so I'm going to take that term and put it right there. But all that matters is that t of n is now O of n to the log base b of a. Question? I put it right here. I'm going to call this c triple prime. N to the epsilon minus 1 and then b to the epsilon minus 1 is in this constant c triple prime. The thing is, we can be loose here because we want to talk about O bounds and omega bounds. We don't have to keep track of that constant. Question in the back. Why do I get to drop this one? Because if I have an upper bound and I bound you, your age is less than 80 minus 40. Agree? So it's also less than 80. So it's also that upper bound right there. It's a low order term anyway, because see, this is log base b to the minus epsilon. Again, this is why you need an epsilon here. So this is a low order term you can ignore. Question? That's right. That's what I do. Yes. At the end of the semester, you're going to be such a master, you're just going to be like slicing through those low order terms and just ignoring them. And which line? This line? How did I get this right here? I'm going to duplicate the page, go to it, oops, and then I'm going to erase this last line right here. And now what I'm going to do is multiply this term right here by this term right here. Okay? So I'm going to get c times n to the log base b of a minus epsilon times minus c triple prime. Okay? I'm going to combine this c and this c triple prime. So see, I have a c double prime. I have a constant there with that low order term. That double prime right there, all it does is it takes into account this guy right here and this guy right here. Did that make sense? The n to the epsilon? Ah, that is important. Because see, I had a minus epsilon right here. I had n to the minus, like blah minus epsilon, times n to the epsilon there. So that's why I got rid of this minus epsilon here. That's why this is the higher order term. Question? Great question. Great question. Because now what I'm going to do is I'm going to flip these signs here, and I'm going to then also show this right here. More questions? Lower bound. Yeah, upper bound. Sorry? Yes. Yes, exactly. You basically just, whatever it takes to make this sign into that sign, and it's a lower bound. Yes, this one, remember I wrote a c prime right here? So this part right here, this f1 plus this c prime is equal to c plus f of 1. So as to your question about this lower bound, instead of taking this entire summation as a hint, just consider this last term. Just say, this is upper bounded by this, so therefore it should be definitely greater than, get rid of all of this stuff. Just consider this last order term, and that will basically do it for you. In other words, this lower bound proof means pick things to delete from this equation, and that's a lower bound, and then that will work out for you. There are more questions. Case 2. When f is in this kind of function, then t of n is in theta I'm not going to go through each of these arguments, but they're very similar to this type of thing. They're similar to this argument right here. What we are going to do in the last few minutes here is go through some examples. Let's use this theorem. Okay, so here's that example I think I had talked about from the beginning of lecture for you to do through induction. Let's do it using Master's theorem. First step, what's f of n? See, this is a thing. We don't even have to compute. We can look at an algorithm and we don't have to, like, is it 9n or 8n? We can just say, well, this is theta of n squared. This part right here? Yes. F of n in this expression is what? Theta of n squared. What's b? What's b? 2. And what's a? 8. And so n to the log base 2 of 8 is equal to n cubed. And so, yes, f of n is equal to O of n to the 3 minus epsilon. So case 1 applies. So therefore, T of n is what? Case 1 applies. So what? Theta. Yes, theta n cubed. Next example. That one's easy. Let's do this one right here. What's f of n? A is equal to 2, b is equal to 2. So n to the log base 2 of 2 is equal to n to the 1, right? So f of n is in omega of n to the 1 plus epsilon. So what applies? Case 3. And so T of n is equal to n cubed. Final example. This is going to be an algorithm we talk about next class. So see you on Thursday.